Hello, hello. Well, welcome. This video is really going to concentrate on how the hypothesis of continental drift became the theory of plate tectonics. And if you remember, we had Wegener's hypothesis of CD, and it was discounted because of other people. Well, lo and behold, after he died in the 1930s on an Arctic expedition, new technologies came about during the 30s and 40s due to World War II, etc. And new technologies came up with new evidences that helped add to his hypothesis. Let's check those out. And the theory of plate tectonics was born based on his hypothesis.
So what we have today is the theory of plate tectonics, which actually includes those four things that Wegener started out with. Without those four things, it would be doubtful that we would have the theory of plate tectonics that we have today. So scientists back in the 50s, 1950s, 1960s started to look at continental drift and started to see how a lot of these ideas were actually really good, particularly with new information that they were finding out after Wegener's death. So heat from the inner core moves outward and creates convection in the asthenosphere. That's something that we're discovering, and the asthenosphere actually moves the lithospheric plates, creating all major features. So all those questions that Wegener had, he was really just missing the piece of the puzzle of knowing that the asthenosphere is a plastic, fluid-like rock material that actually has the ability to flow. If he had had that and knew that, people probably wouldn't have thought he was so crazy.
So plate tectonics really tells us that the mechanism for plates movement, or the top of the earth moving around, is due to the inner core's heat moving outwards, creating convection and moving all the plates around.
You actually have heat moving material. That's just amazing.
That's heat is the key.
Heat is moving the continents.
And the evidence, well, you take Wegener's first four ideas, which are still evidence, and we get four more new ones, which we're going to go into a little bit more detail about. These are much more complicated than Wegener's ideas. And we'll start with a pretty easy one, something we're going to do in class. Basically, they've plotted locations of earthquakes, volcanoes, mountain ranges, and trenches. And when you put those into a map, they tend to be near what we see as plate boundaries today, as we'll find out by the age of the rocks, etc., that we'll learn about real shortly.
The next one is the seafloor mapping, and there's spreading locations. So we've actually been able to figure out the age of the crust through radioactive dating, and we also can figure out through magnetic sensing what the age of the crust is. We just go over it with a boat, and there's lots of different ways to do it. But you can see it in this picture here, where the red material is that newer crust, and as you get further and further away from those deep red lines, you have yellow and green and blue. That's really older crust. But if you look at where the majority of the young crust is, it's in the center of our major oceans, which is not a coincidence.
Those seafloor spreading areas, as we'll learn about. Kind of a tricky one is magnetic seafloor reversals. And basically the key is our positive North Pole has not always been positive. Sometimes the South Pole has been positively charged. About every 120,000 years, the magnetic field of Earth switches. And so sometimes we'll have a South positive pole, and currently, like now, we have a North Pole that's positive. And basically, as new crust is being created or new magma is coming out of the Earth, it's going to harden. And any metal in that magma is going to orient itself with the positive pole, whether it's positive in the north or positive in the south. And then that new rock or new crust is going to get pulled apart. So here it is, let's say, 250,000 years ago. New crust is created, and it's going to be pulled apart, and that new crust now got ripped. Some of it's on the left and some of it's on the right, and since then we had some new crust get created, and it was orientated to the south positive pole, and that got pulled apart, and now we have the north positive pole metal orientating rocks, and that's going to get pulled apart, and we end up with this magnetic seafloor reversal where it's positive to the north, positive to the south, positive to the north, positive to the south, positive to the north, and then we go to the other side of the spreading zone, and it would be the exact same positive trend going on. Kind of confusing, but magnetic seafloor reversals. And here's a closer up view of that magma coming out, hardening right here, and then it's going to get pulled apart very slowly over time, and you get a reversal. North positive, south positive, north positive, south positive, north positive, south positive, Well, hopefully, no pun intended, you get the picture. Woofda.
That picture's right from your book, and some people have a hard time understanding the instructions for that drawing, so we will make sure to go over this part in class as well. And then the 8th thing that we have is radiometrically dated seafloor drill samples. That sounds like a lot. But like what we learned about in our last unit with radioactive dating or radiometric dating, you know, you got carbon-14, which wouldn't be great for this. But you have all those other elements and lead and uranium and yada, yada, yada. We can drill down into the earth, into the rock, and into the ice, and we can figure out the age of things chemically, and we can actually line up all those core samples. And as you approach an ocean ridge, they get younger and younger and younger. And as you go over that ocean ridge, the pattern would be in reverse, and things would get older and older and older as you get away from the ridge.
So we have been able to compile all these data to create a age of the surface of the earth in terms of how old the rocks are. And if you notice, this very light pink and yellow happens to be the last 2.6 million year color. And wherever that light pink and yellow is, happens to be where we can actually go and witness the Earth's crust or plates moving apart from each other. And as you get further away from those spreading centers, the rocks get older and older and older, as you can see color-wise, etc. It's just an amazing thing that's been created since Wegener's been dead due to new technology, but to help take his ideas and make them basically a real theory. What we'd like you to do is create it and do this Venn diagram for class tomorrow. You know, on one area, put everything that's just about continental drift right here. Put everything that's just about plate tectonics here. And if there's ideas, etc., about both CD and PT, put them right in the middle. And bring it to class tomorrow so we can share. For a little review, we're going to hit a couple quick slides. Make sure you have the evidence for plate tectonics, which are all 8 of these, including the 4 evidences for continental drift, and make sure you know what the theory of plate tectonics was solving and how it said it solved the problem of why do we have features where we have features. And the main reason is the H word. And make sure you know what the hypothesis of continental drift was trying to answer and who is the main creator of that. I mean, that's not that bad. You can always review this. Make learning fun. Bye.
Big Al. Yeah.